Hello to everyone, I'm Marco, and here to introduce the project that Francesco, Enrico and I are working on for the Xilinx Open Hardware contest. Aerospace, automotive, professional audio and video application, data storage facilities, industry, medicine, wired or wireless communication and finance are all examples of fields that use hardware acceleration to speed up the execution of their heaviest algorithms. Hardware acceleration, represented by the green area of the graph here, is the process of directly designing on hardware a specific algorithm that otherwise would be run presumably slower on a general-purpose CPU. The best performances would be given implementing the algorithm on a full custom hardware, but in the most of the cases the solution would take so long if compared to what it would take if implemented on any CPU. Now, you may have noticed that we have a rather huge gap in between. So, what about we had something here? Or what about here? Okay, let's see what we have. A good trade-off between performances and programmability is offered by FPGAs, whose behavior can be specified just describing how to link the internal logic blocks they are composed of and how those either combinatorial or sequential blocks should react. Then, so far, we said that FPGAs have competitive performances, a great power efficiency and a good flexibility, but unfortunately they do have a drawback. Configuring an FPGA is quite a hard task and nonetheless time-consuming, as, first of all, the developer needs to be able to design the desired function in a hardware description language, and even then, the design phase is only one of the many configuration steps that require the programmer to learn a dedicated toolchain. If you're really into the topic of programming FPGAs, you might say, okay, fine, but this is why there are high-level synthesis tools. And I'd reply, okay, it's partially right, but while they certainly help a great deal in speeding up the configuration process, their use still requires the developer to learn a dedicated language, often proprietary, as well as linked to a specific board, and this is where our tool comes into play. So, our goal is to develop OXiGen, a tool that completely automatizes the design process, without having the developer deal with data flow concepts that, as just what it said, can be hard to manage. This is the design flow for configuring an FPGA using OXiGen. The input is the control for program to be accelerated, and this is the only phase that the developer should take care of. The next step is the translation of the code in an intermediate representation in order to process it independently of the high-level language of choice. This representation is then provided as input to the OXiGen tool that generates a suitable optimized input for either the Vivado HLS by Xilinx or for the Max Compiler tool of Maxalar Technologies. Are these last two tools that, in the end, take care of producing the bit stream for the FPGA configuration. In the end, OXiGen allows you to obtain the FPGA performances and power efficiency with a fast and easy-to-learn design process. This means that a significant amount of time is saved in the development process, resulting in an increase in productivity. Do you remember the graph I showed you before? And do you think that OXiGen be deserving this spot? Because I do. Well, thanks that you got up to here. Now, if you wish, you can contact us or follow us on our socials. Stay tuned, see you soon!